The various displays available on the control and display unit are selected by use of the rotary selector switch. With the rotary selector on track and ground speed, the left display shows the true track to the nearest 1/10 of a degree, and the ground speed to the nearest knot. Selection of heading and drift angle gives a left display of true heading to the nearest 1/10 of a degree, and a right display of drift expressed as degrees left or right, also to the nearest 1/10 of a degree. For cross-track displacement and track angle error to be operative, a steer between two waypoints must be selected. The left display shows the cross-track displacement from the centre line between the two waypoints. It would look like this. The diagram shows a desired track of 060 degrees. The aircraft is positioned 12 nautical miles to the right of the desired centre line. The right shows the difference between the aircraft track at the present time and the desired track between the waypoints in use. This would look like this. The aircraft's actual track at this time, which is the instantaneous combination of heading and drift, is 20 degrees left of the desired track between the selected waypoints. With the rotary switch at POS, the present position latitude is shown in the left window, and the longitude in the right window. Both are shown to an accuracy of the nearest 1/10 of a minute of latitude or longitude. Selection of waypoint displays the latitude and longitude of whichever waypoint has been selected in the waypoint selector thumb wheel to the nearest 1/10 of a minute of latitude or longitude. With the rotary selector in distance to go and time to go, the left-hand display shows the distance to go to the nearest nautical mile, and the time to go to the nearest 1/10 of a minute from present position to the two waypoints along the route, between the two waypoints selected in the From To LED display. The time to go is calculated from the present ground speed, and the system is responsive to changes in ground speed. If the thrust is reduced, as the speed trickles off, the operator can see the time to go increasing as he watches. With wind selected, the left window shows the wind direction to the nearest degree, and the right one shows the wind speed to the nearest knot. In order to calculate wind velocity, 4 inputs are required. These are heading, drift or track, ground speed, and true airspeed. The INS generates the first 3 itself. It is necessary to have an input of TAS from another source in order to calculate wind velocity. On its own, INS has no facility for calculating TAS. However, any aircraft which has an avionics suite sophisticated enough to include an INS will also include an air data computer, which will provide the TAS to the IN. DSR Track STS stands for Desired Track and System Status. The desired track is the initial great circle true track between the waypoints selected in the From To LED display, and is shown to the nearest 1/10 of a degree. We mentioned earlier that system status can give an indication of time remaining to align. However, once nav has been selected on the MSU rotary switch, STS is used to indicate serviceability and for fault diagnosis. If the INS is serviceable, a code, usually 0000, appears in the right-hand LED. Its main use, however, is for fault diagnosis in conjunction with the red WARN light. The INS carries out a continuous process of self-monitoring as part of its operating routine. If any malfunction is detected, the WARN light illuminates. The WARN light simply indicates that there is a failure. It does not tell the operator what it is. To diagnose the fault, select Desired Track, System Status. In the right-hand window, a 4-digit status code will be indicated. This 4-digit group is used in conjunction with the pilot's operating handbook. In the malfunctions checklist, there is a table consisting of 3 columns. The first gives the numerical code, the second identifies the failure, and the third gives the appropriate action to be taken. Finally, the test function is used for deeper diagnosis by the maintenance personnel and is not normally used by flight crew. Selection of test causes all the lights to light up and puts an 8 in every LED, since 8 is the one number that uses every element of the 7-line display. This can be a useful function if you suspect that an LED in a number display is faulty. For instance, a 7 can appear as a 1 if one LED element has failed. On pressing the Hold button with the rotary selector in POS, the LEDs freeze and the Hold button lights up. On pressing the Hold button a second time, the light goes out and the display unfreezes to the new present position. Whilst the Hold light is on, it is only the display which is frozen. The internal calculation of present position continues. We'll now look at the yellow CDU battery light. It is essential that electrical power to the INS is not lost, even briefly, during flight. If it were, computing would stop and alignment would be lost. As we have already discussed, it is not possible to align in flight. The aircraft must be stationary on the ground. Therefore, in the event of INS power failure, all computing and navigation facilities will be lost until the end of the flight. This must not be allowed to happen, and so the INS contains its own battery, which is constantly charged from the aircraft power supplies. In the event of an aircraft mains power failure, the battery simply takes over, and power supplies to the INS are maintained. This is indicated by illumination of the CDU bat light. The battery will last for a reasonable period of about 20 to 30 minutes, during which time the crew should attempt to reconnect aircraft main power. There will be a fault-finding checklist, which will vary from aircraft to aircraft, usually along the lines of check the circuit breakers, then check the fuses, then try resetting failed alternators, generators and inverters, and finally try switching to an alternative buzz bar. If any of these succeed in returning the aircraft main power, the CDU bat light goes out. The situation is recovered, the battery is recharged, and no harm has been done. Otherwise, the MSU red battery light will shortly appear. There is also an MSU red battery light. As we said, the battery has only a limited charge. If the voltage drops below a specified level with time, the INS functions can no longer be preserved. In this case, the MSU battery light illuminates. This is more serious. It means that the battery is the sole source of power to the INS, and that the battery is failing. When the battery power drops below a predetermined level, alignment is lost and, in time, all INS facilities will be lost. Even if power is subsequently restored, it will not be possible to realign and all navigation computing functions remain lost. We now come on to the attitude reference function. There may be occasions when full navigation computing is not available, but the gyros are serviceable. This could be in the event of a computing malfunction so that earth rate and transport wander corrections cannot be calculated, or it could be after an alignment failure in flight. On many aircraft, the gyros are used as primary attitude information, as well as for inertial navigation, and it may be possible to retain gyro information. This is done by selecting @ref on the MSU, which disconnects the computing and loses alignment if this has not already happened anyway. The accelerometers now act as gravity switches, as they do during the levelling phase of alignment, and the gyros become gravity tied in the long term. They become earth gyros. The system now gives attitude information and a limited form of heading. The gyros are normally very accurate, but there is no correction for earth rate and transport wander, and the heading needs to be reset periodically to an independent source, which is usually a magnetic compass. In effect, the gyros are acting as a super-accurate form of DGI and as an attitude indicator. That completes the lesson on INS operation, so we'll summarize what we've covered. Selection of standby on the mode selector unit connects aircraft power to the IN. It also allows present position to be entered. Moving the MSU to a line starts the alignment process, which continues automatically for approximately 17 minutes, depending on the latitude. On completion, the MSU Ready Nav light will come on. However, it is also possible to align with the MSU selected to Nav. Once alignment is complete, we select Navigate. The alignment is now protected and the aircraft can be taxied or pushed back. If the system operates normally, it will now remain in Nav until final shutdown. Attitude reference, or ATREF, as the position is labelled, is used only in the event of a computing malfunction or loss of alignment. It maintains the operation of the gyros, but all computing and alignment is lost. It gives attitude and a limited form of heading. We then looked at the control and display unit and went through each of the rotary switch functions. The alert light gives warning of approaching waypoint changeovers. The warn light is used to indicate malfunctions. And the CDU battery light tells us that we have lost aircraft power to the IN, and that the IN's own internal battery has taken over. However, if the MSU battery light comes on, we have lost INS alignment and computing for the rest of this flight. Waypoint 0 gives us the facility to steer directly to a waypoint from present position instead of a longer route. And the Hold button freezes and unfreezes the present position display. We also mentioned that the INS needs an input of true airspeed if it is to have the facility to compute wind velocity. Now that we know something about INS theory and also practical operation, we can go on to look at errors in the next lesson.